This is the third video about the Christoffel symbol, and in this particular video we are going to discuss about the deriving the Christoffel symbol for the metric tensor in the 3D space. So we have derived the metric for the flat 3D Euclidean space in our previous video. You can check out that particular video, and you know that if we know the metric, we can generally derive the Christoffel symbol. But what actually the meaning of the Christoffel symbol also I'm going to discuss in the brief. So the sign is like this: capital gamma. This is the capital gamma. Indices are jk and one upper indices is I. So the Christoffel symbol has a very deep physical meaning. First of all is that it tells how the basis vectors are changing. It means this Christoffel symbol I indices jk tells about the changing of the, let me write first here, then I will explain this. So this is the expression for the Christoffel symbol. You will say what the expression is. So the simple meaning of this particular equation is that the Christoffel symbol, here I and jk, measures the change in the j. The change in the j basis vector with respect to the k basis vector in the direction of I basis vector. What I mean, you know, this is partial derivative, it represents the change. So the small change in the basis vector ej, okay, subscript j, with respect to the this particular basis vector in the direction of E hat I. So this is the meaning of the simple meaning of the Christoffel symbol, and you can see that it tells us about the changing of the basis vector, how the basis vector are changing. Generally in the Euclidean space, or general when we study about the physics, we assume that our basis vector, which are I cap and j cap, is same everywhere. I cap is same everywhere, j cap is same everywhere. But in the 3D curved space, in the curved space, we can say that this is not always true. Maybe the basis vector changing, and that's the meaning of the Christoffel symbol. It measures the change in the basis vector. So in this particular video, basically we are going to derive the Christoffel symbol for the flat space, then we will move to some advanced metric where we'll derive it for the curved space. Okay, so let's start. First of all, we have to write down the Lagrangian. So first of all, let me introduce you the two methods. First method is using the metric tensor that we have derived, Gij, grr, gr theta, gr phi, g theta r, g theta theta, g theta phi, and the last is g phi r, g phi theta, and g phi phi. So this is our metric for the this is our metric for our flat Euclidean space, in which you can identify that most of the components, like this particular component, these two components, and these two components, all of them are 0. One minute, not this component, let me clarify. 1 minute, I have chosen the wrong one. Okay, so this and this, so 1 2 3 4 5 and 6. So out of 9, 6 as a 6 metric tensor is equals to 0. Only the 3 diagonal components, as you can see here, have some value in the polar coordinates, which is equal to this: 1 0 0 0 r square 0 0 0 r square sine square theta. So this is our Christoffel. Well, let me erase it. 1 minute. Sine square theta. So this is our metric tensor for the flat Euclidean space in the polar coordinates. In the Cartesian system, it's different, but in the polar coordinates, it's like that. So there are actually two methods for deriving the Christoffel symbol. So let me erase this because you all know this. So what are the methods we can use to derive the Christoffel symbol? So actually there are two methods. First one is very lengthy, very. First one is directly computing it from the formula, and the formula is ijk is equal to the 1 by half gil, and the derivative of g, let's say first of all jk divided by del xl plus del jl divided by del xk and plus del lk divided by del xj. So this particular Christoffel symbol. So this is the formula of the Christoffel symbol. You can choose the metric because you know that only 3 of the components of the metric are non-zero, and beside that all of them are 0. So you can generally use this formula, but the fact is that it's very lengthy to use this particular formula. So I have one very different and one very intuitive method to find out the Christoffel symbol, which is using the geodesic equation. You will say, how using the geodesic equation? So this is first method, and the second method which I will use in this particular video is using the geodesic equation. So first of all, let me recap that what was our geodesic equation. It was x double dot tau plus Christoffel, 1 minute, plus Christoffel symbol tau mu q dot nu. Okay, so this was our geodesic equation that we have derived, and the derivation that we have used in the, I guess, first video. You can check out that particular video for the derivation. And this is our particular example of the geodesic equation. What we will do is that we will construct the Lagrangian. Yes, you've heard it right. We construct the Lagrangian and then we can equate with the geodesic equation. What I'm trying to say is that I can construct the Lagrangian of the particle, then the Lagrangian also yields the equation of motion, and the equation of motion will be like in this particular form, and by comparing the equation of motion deriving by the Lagrangian, we can find out the different components of the Christoffel symbol. Most of the Christoffel symbol components will be 0, but let's see. And the second method which I'm going to use. So remember this geodesic equation, I've derived it in the first video. You can check out that particular video. So first of all, we have to construct the Lagrangian. So Lagrangian is equal to 1 by half mass into velocity. So we are going to write down the velocity in the form of polar coordinates. So you have to do some little mathematics, and by the differential form of the polar coordinates you can derive the velocity, which is equal to 1 by half into velocity square can be written as r dot square plus r square theta dot square plus this theta I have to erase because you will get confused. So let me write in a clear fashion. R square theta dot square, dot mean the time derivative, and plus r square sine square theta, and here it should be phi dot square. Dot again means the time derivative. This is a basic. Okay, so this is our Lagrangian. So what I'm going to do is that I'm going to differentiate the Lagrangian first of all with respect to the r, then with theta, and then with the phi, and the 3 equation of motion equations that we will see, we can equate that with this particular geodesic equation. This particular geodesic equation we can equate. So first of all, what we are going to do is to differentiate the Lagrangian, and the formula is d by dt of del L by del R first, then minus del R dot del L by del R is equals to 0. What we are going to do, let me write it. Okay, first of all we will do the del L by del R, and which is equal to, you can follow as this basically 1 by half mass into, this will become 0, this will become 2r theta dot square, it will become plus 2r sine square theta phi dot square. Okay, so this is our del L by del R. Second, del L by del R dot, this is del, 1 minute, right? So this is del R dot, and del r dot will be, again using this particular equation, when we differentiate, this term will become 0, this term will become 0, and the only term we are left is with the 2r dot. Now we are going to take the time derivative, d by dt of del L by del R dot, and it is equal to the 2R double dot. And here it should be 1 by half and m. Okay, 1 by half m. Okay, this is a thing, and again here 1 by half and m. Now we'll write the Lagrangian equation. So 2 and 2 here will cut out. So d by dt, which is r double dot m minus this equation. So we will take 2 common, then 2 and this will cut out. What we are left, and also m also cut out. So we will try to do write as m into r theta dot square plus theta dot square plus r 1 minute plus r sine square theta phi dot square. So here let me clarify that here it is not, let me write it as m r theta dot, okay, m r theta dot square. So this is our equation, and after we will cut down m, and here it should be also m, I have not written it, sorry. So this is equal to r double dot minus r theta dot square, and here should be minus, sorry for this basic mistake, minus m and n cut out, it will minus r sine square theta phi dot square is equals to 0, So this is our equation of motion. Yes, this is our equation of motion. Now we are going to compare this with our Christoffel symbol, and you will say how, with the geodesic equation, and you will say how. So let me do this. So the equation was x double dot tau plus Christoffel symbol, 1 minute, Christoffel symbol tau I j q dot I q dot j. Okay, now if you see the comparison here, in the place of x double dot tau there is r. You are saying it? Yes, there is r, and in the place, let me write it using the equation that this r double dot plus r can be written as r theta dot square, and plus this will be Christoffel symbol r phi theta dot square is equals to 0. 1 minute, is equals to 0. What you will see is that here I have written this Christoffel symbol r theta in place of minus r, and here I have written the Christoffel symbol here r and phi in place of minus r sine square theta. You can see that. So you will say that okay, so it means these are the Christoffel symbols. So yes, these are the Christoffel symbols. Then you will say how we can find this. So you can find this using this particular rule, that here q dot I and q dot j are played by the role of this particular theta dot square. It means is also the fact that I and j here are theta and theta respectively. That's why you can see that in formula I have written theta. And the second situation you can see that is phi dot square. It means the phi dot square is the role played by this. It means our indices I and j are also phi, and you can see that here I have written phi. So ij is theta and ij is phi. So you can see here I have written two Christoffel symbols here using the comparing with the geodesic equation, and these are the two very important things. So let me write down what we have obtained. So we have obtained the Christoffel symbol r theta is equals to minus r, and Christoffel symbol r phi as minus r sine square theta. So yes, this is our Christoffel symbol